Hey guys, this is the PowerPoint for 3.4. 3.4 is applications of the derivative in business and economics, right? So just like in 3.3, we're applying the derivative, and that was optimization problems. Here we're going to do it for business and economics. So what does that look like? We'll talk about marginal cost, revenue, and profit. Hopefully that's something you're familiar with. We'll talk about maximizing these things. We'll introduce something called inventory cost, economic order quantity, EOQ, and elasticity of demand. All right, so let's refresh ourselves. Hopefully it's a refresher anyway. If not, here we go. Marginal cost, revenue, and profit. So remember that marginal change of a function is given by the derivative, and it approximates the change in your function when x increases by 1. All right, so if we're talking about not just any function, but the revenue function or the cost function or the profit function, we call that the marginal revenue, cost, and profit respectively, and those are just given by the derivatives. One thing to notice, since profit, hopefully you remember, is revenue minus cost, P prime is R prime minus C prime, right? So if you know just the revenue and cost, you can form the profit function, then take the derivative, or you can take the derivative separately and subtract. Either way is just as good. All right, let's look at an example of marginal profit. All right, so it says penny is determined that in order to sell X pies, the price per pie must be little p of X is 1,000 minus X. It also says the total cost of producing X pies is given by C of X is 3,000 plus 20X. And we're going to have three parts. The first part here says find the total revenue and the total profit. So remember revenue, R of X, right? So your revenue, that's how much money you take in, right? How much money is in the cash register at the end of the day. So if we're just talking about selling just pies and we charge the same price for all of them, then how much money do we have at the end of the day? Well, we take the number of pies we sold, we multiply that by how much we sold each pie for. So what does that look like? Well, that looks like the price, that's how much we sold each pie for, that's P of X. That's a lowercase p, and we'll use the capital P for profit. So the lowercase p of X, that's the price, and then how many things did we sell? Well, we sold X of them. So the revenue is going to be given by the price times X. So that's 1,000 minus X times X, and distributing that X through, we get 1,000X minus X squared. So there's our revenue. We're also asked to find the total profit. So remember, profit is revenue minus cost. So you guys can double check me on this, but if I take a revenue of 1,000X minus X squared and subtract 3,000 plus 20X, which is our cost function, so what do we get? So I'm just going to denote for you guys, this is revenue minus cost. But I got 980X, so that was our 1,000X minus 20X. The minus X squared from the revenue, and then the minus 3,000 from the cost. So that is our profit function. And that's all of part A, finding those two guys. Part B says, how many pies must Penny produce and sell in order to maximize the profit, and what is the maximum profit possible? So here we've got just a function P of X, and we want to find the maximum profit. So that's something you all should be pretty familiar with, because that's what we did in 3.1 and the same sort of optimization techniques from 3.3. So I'm going to let you guys pause the recording here, try this on your own, and then see if you can get the same answers I did. So go ahead and pause it and try it on your own now. Okay, so let's see, what did you guys get? Well, hopefully you took the derivative and you found your critical value, and for that critical value you should have gotten 490, right? X equals 490. If you didn't get that, double check your work, and if you're not sure, go back and look at what we did in 3.1 in order to determine a maximum or minimum of a function. So we took the derivative, which was 980 minus 2x. We set that equal to 0, and that gave us x equals 490. You do have to double check here that this gives you a max, and the easiest way to do that is to use that second derivative test, which would give you the second derivative is -2, so it is a maximum. So all that work needs to be shown, but I'm going to let you guys do that on your own here. When you do all of that work, you get x equals 490 is a maximum. So one more time, if you just write this on a quiz or an exam, that's not enough work. I'm assuming you guys did all that behind the scenes, but I wanted you to do that on your own. So when you get this 490 and you check that it's a maximum, well, that's exactly how many pies Penny must produce and sell. So x equals 490, that's how many pies. So sell 490 pies to give a maximum. And then it says, what is the actual maximum profit? Well, that's where you take x equals 490 and plug it into the profit function that we formed in part A right there. And again, I'll let you guys double check that. But I got a maximum profit of, let's see here, max profit. I got 230, no, make that 2,371,100. 237,100. One more zero. Whoops. So double check that there. That was the maximum profit, and that's just plugging in x equals 490 into here. Okay, so that's part B. Part C says, what price per pie must be charged in order to make that profit possible? So the price, that was the little p of x, that function I just underlined at the top. So if x is 490, then p of 490 would be 1,000 minus 490, which is 510. So she must charge 510 per pie to get this max profit. So those must be like really, really good or just really, really large pies, right? Whatever that might be. So that's part C. Move on to inventory cost. So inventory cost is, let's say you're running a shop or a business, it's literally the cost of keeping and maintaining an inventory of things to sell. So that looks like two things. There's something called a holding or carrying cost, and that's a cost from just keeping X things, right? Whether it's storage or insurance, or maybe it's things that can spoil, or it's breakables, anything like that. H of X, that's the holding cost, the cost of just keeping X things. X here, the number of things, is called the lot size. So that's your lot size. So you'll be asked things like, what is the minimum lot size? So we're looking for something like that. That's how many things you have. There's also a reordering cost or an ordering cost, and that's just the cost of X things to place an order for them. So your total inventory cost is C of X, is just adding these things up. In your homework, you might be asked to find the total inventory cost, and in your book it does tell you how to form that, but we will not be doing that. So for example, I know in 28 it says what is the minimum inventory cost. That's on the homework. You don't need to answer that question. You just need to find the minimum lot size, things like that. But we're not going to actually form this total inventory cost function at all. There's a few formulas in the book that you can find if you're interested, but we won't be doing that. Anyway, so why do we care about this? So bear in mind, the whole point of this is that your inventory cost is just C of X, it's your cost. So let's move on to what's called the economic order quantity, right? So remember, we are in this situation of we've got a cost function where it's C of X, and X is our lot size, which is the number of things we're going to keep on hand, X things, right? So economic order quantity, that's the order size. So if you're going to place an order for things, it's the quantity of things you're going to order, that when you order that many things, it's going to minimize the holding and ordering cost for your entire year, or whatever it is. So the economic order quantity is the size at which you want to place your orders, and it's going to minimize the cost of the order combined with the cost of holding on to the things. So for example, you don't want to order just a billion things because it's going to cost maybe a whole lot to hang on to a billion things. Maybe you order only 1,000 things. That's going to bring down your order cost and bring down your holding cost. So there's a nice medium somewhere that's going to be the perfect quantity that minimizes your total cost. That's the economic order quantity. The important thing here, since we're minimizing cost, this economic order quantity, it's a value of X. It's a critical value. You can do a lot of work to get to the following. The economic order quantity is given by this equation here in terms of cost per order, units sold, and carrying cost. You don't need to know how this came about, but it's in the book if you do care. The point is it's a critical value and it's a minimum. So if you're asked what is the economic order quantity, or maybe something along the lines of how many times should the retailer reorder and what should the lot size be in order to minimize cost, right? So economic order quantity is the lot size that minimizes cost, right? I'm trying to stress that. That's all it is. It's literally the size of your order that's going to minimize your cost. So if you're asked to find anything like that, you're going to want to use this equation to find the economic order quantity and then use it to answer whatever question you're asked. But there it is. You can reference it as needed. Look at an example of this. So this says a company anticipates selling 3,200 units of its product at a uniform rate over the next year. Each time they place an order for X units, they're charged a flat fee of $50, and the carrying costs are given $32 per unit per year. So we're asked, what is the economic order quantity, right? So remember, that's the order size that's going to minimize your cost. So all you have to do is plug that in, everything you know. So X is the square root of 2 times, and then what's your cost per order? Well, that's this, every time you order, you're charged $50. So that's 2 times 50 times units sold. Well, it says they're going to sell 3,200, so times 3,200. And then divided by carrying cost per unit, that was 32, so over 32. So what is that? Well, I got that is the square root of 10,000, which is 100. So when you order 100 things per order, that's your lot size. That's going to minimize your cost. That is your economic order quantity. So that's just plugging things in. Part B says, how many times should they reorder each year, and what should the lot size of each order be to minimize the cost? Well, how many times should they order each year to minimize cost? We want to order 100 things a year, and we want to sell 3,200 things. So if we want to sell 3,200 things and order 100 things each time, that's 32 over 100, which is, 3,200 over 100, which is, I gave it away, 32. So if we order 32 times a year, that's going to minimize our inventory cost. So that answer is 32. And it says, what should the minimum inventory cost be? Well, that's exactly your economic order quantity, just rephrased, and that was 100. All right, let's move on to something called elasticity of demand. So maybe you've heard in your business classes already this idea of elasticity. If not, let's talk about what it is. So elasticity is a measurement of how two things are related, right? So it measures value of one thing compared to value of another. So you can read this, but before you do, let's just go through an example. So just coincidentally, whatever it may be, but studies and records have indicated that the price of bread and the price of milk are related to each other in what is called an elastic way, where if bread goes up, milk goes up by about the exact same amount. Those have always been sort of related. You can imagine another sort of elastic relationship would be the price of oil and gasoline, right? If oil goes up, gas prices are going to go up. If oil price goes down, gas prices are going to go down. Compare that to, say, the price of bread and the price of oil. Changes in oil price are not going to have much effect on the price of bread. So that relationship would be called inelastic. So those are our sort of examples to keep in mind. But basically what you have here is that if you change 1%, change the input variable by 1%, and you say large change in the output, that's called elastic. So the more elastic something is, that means a 1% change in the first variable creates a large change in the second. We call something inelastic if that same 1% change in the input variable causes a relatively small change in the output variable. All right, so elastic if they're related, where a small change, a 1% change creates a really large change, and inelastic if a small 1% change creates almost no change. So that's elasticity of anything. If we're talking about specifically demand and price, we call that elasticity of demand and denote it by eta. So this elasticity of demand can be given by taking the percent change in demand, right? Q for quantity, that's the demand, and dividing it by the percent change in price. Right, so that looks something like this. Don't worry about that. Let's just move on and see where all this came from. If we take what we had and take the limit as the price changes go to 0, hopefully that reminds you of an instantaneous rate of change where we used to take the limit as h goes to 0. And that's exactly what we get, and we call that the point elasticity of demand, the instantaneous rate of change of the elasticity of demand. And when we do that, we get P over Q times dQ dP. So this here is an implicit derivative with respect to P. And we now start calling that epsilon. Epsilon is the point elasticity of demand. But wait, bear with me one more time. Because if we actually define it the way I just did, we always get a negative number, and that's really annoying. So what we're going to do is take exactly what we just had, but stick a negative sign there. And this equation is one that I'll give you on exams and quizzes and whatever, but you do have to know how to use it. So if I say here is Q in terms of P, and I give you an equation and say find the point elasticity of demand, I will give you this equation. You have to know how to use it. What is this? Well, the point elasticity in demand, like we were talking about, it tells you how the demand changes, at what percent the demand changes when there is a 1% change in price. So you change your price by 1%, whatever epsilon is, that's the percent at which your demand changes. Let's look at an example. So we have that a company estimates the weekly sales Q of its products is related to the price by Q is 4,500 over the cube root of P squared. It says currently each unit of the product is selling for $27. Determine the point elasticity of demand, and then I give you that equation. Again, I'll give you that equation on a quiz or an exam or whatever. You do not have to memorize it. I will give it to you. So how do we do this? Well, in order to plug things into this, we need P, which is here, and we need Q, and we need dQ dP, and that dQ dP should be a number, which means we need to find dQ dP and then plug in whatever we need to turn that into a number. So what is P? Well, we're given currently the price is $27, so P is 27. We need Q when P is 27. So what we do is we take this equation for Q and plug in P equals 27. I'll let you guys try that on your own. Pause the video if you need a second. I got Q is 500. And lastly, we need to find dq dp. So let's take this equation. If we take the derivative of this whole thing with respect to p, on the left side, we'll get exactly dq dp, which is what we want. And on the right side, we'll get something else. So try that on your own again and see what you get. Again, pause the video if you need to. All right, so on the left side, we get dq dp. On the right side, remember we can write this as 4,500. That says q is 4,500. And then how do we write over the cube root of p squared? Well, we're going to write that as p to the negative 2/3. So when we take the derivative, we'll get negative 2/3 times 4,500. That's minus 3,000. And then p to the negative 2/3 becomes p to the negative 5/3. So there it is. There's dq dp. But since we want a number here, we really want to evaluate this at p equals 27. So that's dq dp. There's a q there. I know it doesn't look like it. And then we do this evaluate at p equals 27. And when we do that, you guys can double check, but I got a fun number, negative 3,000 over 243. I say it's a fun number because it's actually a repeating number, and it's about, that becomes negative 12.3. But that number is actually 12.345790, and then that repeats. So it's all of them but 8 and in a row. So that's cool. I know you guys all think that's fun. But anyway, so there's dq dp. Now all we have to do is plug in p, which is here, q, which is here, and dq dp, which is there. So epsilon is minus 27 over 500 times negative, and I would use the whole fraction here, so you get an exact answer, over 243. And I got, again, double check me, but I got exactly 2/3. So my point elasticity of demand is 2/3. There it is. Okay, so now let's look at the difference between elastic, inelastic, and unit elastic. What are those? What do they mean? So if R of P, which is our revenue, whenever P is our price, well, that's just the quantity times the price, Q times P. If that's R of P, then the product rule gives all of this stuff for the derivative. And the point is that if I kept going, I could get to something that looks like this. And again, don't even worry about that. Let's just look at what all this means. This is all behind the scenes. You can ignore this slide if you'd like. And you get to this one. This is the important one. So if epsilon is greater than 1, then the derivative of the revenue is less than 0. So the marginal revenue is less than 0. That means that when the price increases, the revenue is going to go down, right? The rate of change of the revenue, R, with respect to the price is negative. So when the price increases, the revenue is going to decrease. And when the price decreases, the revenue is going to rise, right? So the rate of change of the revenue with respect to the price is negative. So the revenue is going to do the opposite of what the price does. And here we say that that is an elastic demand, right? We're talking about elasticity of demand. So here this is elastic demand whenever the epsilon is greater than 1. If epsilon equals 1, then the derivative would be 0, which means the rate of change of the revenue with respect to the price is 0, which tells you that the revenue does not change when the price changes. And here, that is called unit elastic. So if epsilon equals 1, we are unit elastic. Lastly, if epsilon is between 0 and 1, you should realize that epsilon's never going to be a negative number. We set it up that way. It's also never going to be 0. So if it's between 0 and 1, then that means the rate of change of the revenue with respect to the price is positive, which means that when the price increases, so does the revenue. And when the price decreases, so does the revenue. So here, when epsilon is between 0 and 1, we say it's inelastic. Demand is inelastic. So to recap, if epsilon is greater than 1, demand is elastic. So if I say epsilon is 3, is demand elastic, unit elastic, or inelastic? You have to know that when epsilon is greater than 1, for instance 3, demand is elastic. If epsilon equals 1, we are unit elastic, and if epsilon is any number between 0 and 1, then demand is inelastic. All right, so that's something you guys are going to have to memorize. An example says a company determines that the point elasticity of demand for one of its products is 2.6. Is demand elastic, unit elastic, or inelastic? Well, based on our last slide, 2.6 is greater than 1, so demand is elastic. It also says if the price of the product is raised by 1%, will the company's revenue increase, decrease, or remain the same? So the price is raised by 1%. So the price is raised. So we're talking about an elastic relationship when epsilon is greater than 1. Then if the price... Our last example is a little bit different, but it's similar. It still uses point elasticity of demand, but here we're going to come up with an actual number for revenue. So let's look at that. It says for a particular commodity, epsilon is 1.6, and currently we're selling 150,000 units for $20 each. It says how does a 1% increase in price affect the revenue? So for this type of problem where you're given current units and current price, and it says how does it affect the revenue, the answer we're looking for is something like revenue increases by however many dollars or decreases by however many dollars. We're not just looking for it increases or decreases, but we want a specific number here. So just for comparison, in your homework, that's the difference between like 1 through 8, where it might just ask what is demand, is it elastic, inelastic, unit elastic, and 20 and 21 that say will the revenue increase or decrease or remain the same. Those are just, you would say, increase, decrease, elastic, inelastic, whatever. For numbers 9 and 10, however, those are the ones where it gives you a current level of production and a current price, and it asks for how it affects the revenue. So for those types of problems, you have to do the following, which is to give an actual difference in revenue. Anyway, so let's continue. So one thing to notice first is that epsilon is 1.6, which is greater than 0. So we're looking at an elastic relationship. And so that means since I'm elastic, if I'm increasing the price by 1%, I should expect that the revenue is going to decrease. So for an elastic relationship, it's going to do the opposite. So if the price increases, I should expect the revenue to decrease. The question is by how much? The answer is not this 1.6. What this 1.6, remember, this is the point elasticity of demand, which tells you how the quantity changes or your demand changes as the price changes. What that 1.6 represents, that is the percentage that your demand is going to decrease as the price increases. Demand is always going to decrease when price increases, right? If a price goes up, people aren't going to buy as many things. It's not going to be as popular, whatever it is. This point elasticity of demand tells you how demand decreases, at what percent it decreases when price increases by 1%. Okay, so for all of that, we want to know how it affects the revenue. So to do that, to determine how it affects the revenue, first we need to figure out what is the revenue right now. So I'm just going to use R to represent the revenue right now. So you guys should know the revenue is given by number of things times price per thing. So that's 150,000 times 20, which is 3 million. So our current revenue is $3 million. What we want to do is use this point elasticity of demand to give us a new revenue. And to get our new revenue, we'll need a new price and a new quantity. So let's first come up with a new price. So I'm going to just say here, new stuff. The new price, well, we know we're increasing the price by 1%. So we're going to start with our old price and then add 1%, which is 0.01 times the old price. So that's 20 plus 0.01 times 20. So the new price is 20.2. So again, we took our old price and we added 1% of our old price and got 20.2. For our new demand, new quantity, Q, we take our old demand, or our old quantity, which was 150,000. And here, demand is always going to decrease as price increases, so we're going to subtract, and that's where we use this 1.6. So we're going to take 1.6%, so that's 0.016 times our old quantity. So we start with the old quantity of 150,000, and we want to subtract 1.6% of 150,000. I'll let you guys double check me here, but I got 147,600. So that is our new quantity and new price. So that means our new revenue is those two numbers multiplied together. And again, you should double check me, but I got 2,981,520. And that's in dollars. So that's our new revenue. All right, so one thing is, since we had an elastic relationship where epsilon was greater than 1, we definitely expected the revenue to decrease, so it's good that that's what we got. But we want to answer here by how much it decreased. So you do 3 million minus that 2.9 whatever million. And the answer we got is that we got a decrease. So it says, how does it affect the revenue? The revenue is going to decrease by, and when you subtract those two numbers, you get 18,480. And that is the answer we're looking for. Not just that it's going to decrease, but by how much it is going to decrease. There is the end of 3.4, and I believe for this one I didn't delete any of the problems off the homework list. I kept them all because there weren't very many of them. So make sure you guys come to class with questions over these notes, maybe these examples I did, or if you start that homework.